This monitor uses liquid crystals to display images. How this thing works amazes me. Let me show you. Let's start at the back of the screen. If you look here, you'll see a row of LED lights at the bottom called the backlight. These are the only lights in the monitor. Next, I'll put in what's called the optical system, which makes the light even across the back of the screen. Now, the first sheet makes a nice, even white background for the light. The next piece is called a light guide plate. You can see it's covered with dots. When light enters from the bottom edge, it propagates down the plate by total internal reflection, unless it hits one of the dots. And they make some of the light rays emerge out of the front. Then engineers place a diffuser film. It helps eliminate the dot pattern from the light guide plate. Then comes a prism film. You can notice here that where I have the sheet, it's much brighter than where it isn't. So at this point, if we put the last diffuser film on, we have a very evenly lit surface, all from the single row of LED lights at the bottom. The backlights are always on, but what controls what we see is this piece of glass. It functions as a shutter. At the back and front of the sheet are two polarizers. They stick tightly to the piece of glass, but let me illustrate it with two sheets that I have. If I lay this sheet on the optical system, you can see that it passes light. And if I put this piece on top, it also allows light to pass. But if I rotate it exactly 90 degrees to the bottom sheet, you'll see the light disappears. The bottom sheet creates polarized light, which will only pass through another polarizer set to the right angle. Now, of course, in this LCD monitor, the front polarizer doesn't rotate. Other than the on-off switch, the monitor has no moving parts. Instead, what we do is we place these two polarizers 90 degrees to each other, this configuration that allows no light through. And then, if we want light to pass, we twist the light within the glass pane to match the front polarizer. How? Well, it's the simple-looking piece of glass that does all the magic. Let me put it back on, and you can see that the image reappears. I just love that. It's actually a sandwich of glass. Engineers fill the space between the panes with tiny glass beads to keep them separated, and with organic molecules known as liquid crystals. The crystals have interesting properties in that they do not allow light to pass uniformly along both axes. Grooves are formed on the surface of both pieces of glass at 90 degrees to each other. The molecules in between line up in a beautiful helix. When light from the backlight passes through the first polarizer and enters the sandwich, it's rotated by the liquid crystals so as to allow it to pass through the second polarizer and emerge out the front of the screen. This is known as the normally white mode. Applying an electric field across the sandwich causes the crystals to line up lengthwise. Now, the light that passes through the front polarizer is not rotated by the crystals and can no longer pass through the front of the screen. We call this the normally black mode. Now that we can control the light through the glass, how do we get color? Let's look in detail at the piece of glass. By controlling the voltage between these transparent electrodes, we can control the intensity of the light that passes through. Now, there's much more to the glass plate. Let's examine this section where my sleeve meets the gold background. If we zoom in, you can see it's made of pixels. If I turn off the image and backlight the glass sandwich, you can see the screen contains red, green, and blue sections. These are subpixels. The three together make a single pixel. In the sandwich, they are simply colored tiles that overlay the front transparent electrodes. They follow the RGB color model. We adjust the electrode shutter behind the subpixels so that they make up a particular color. For example, to get the color of the blue in my shirt, we set the red subpixel to 12% of maximum intensity, green to 21%, and blue to about 50%. And now for the last critical piece in the glass sandwich. On the back pane, engineers paint tiny devices called thin film transistors. That's why these monitors are often labeled TFT. Each subpixel has a transistor which controls it. This transistor you see here functions as a switch that allows the screen to be updated row by row. By applying a voltage to a specific row while keeping the other rows grounded, we allow each subpixel in that row to receive video data coming from the top of the screen. Only one row can receive information at a time, but the speed with which this happens for each row is so fast that your brain blends it into a fluid image. What an amazing device, and also the technology that allowed computing to go mobile. Imagine laptops, cell phones, and tablets without lightweight screens. I'm Bill Hammack, the Engineer Guy.